Hey everyone! If you've ever done heat transfer analysis or worked with CFD tools like ANSYS Fluent, you've definitely come across something called the Nusselt number. But what exactly does it represent? Why is it so important in convection heat transfer? And how is it actually used in CFD simulations? In this video, we'll break down the Nusselt number, its physical meaning, and its real importance in CFD applications in a simple and intuitive way. So first things first. The Nusselt number, denoted by nu, is a dimensionless number used in heat transfer. Mathematically, it is defined as Nusselt number equals ratio of convective heat transfer, conductive heat transfer. In simple words, it tells us how effective convection is compared to pure conduction. If heat transfer were happening only by conduction, the Nusselt number would be 1. If convection enhances heat transfer, the Nusselt number becomes greater than 1. So higher Nusselt number means better heat transfer performance. The most common formula you'll see is nu equals H times L over /K, where H equals convective heat transfer coefficient, L equals characteristic length, K equals thermal conductivity of the fluid. This equation directly links fluid flow, thermal properties, and geometry, which is exactly why it's so important in CFD. Let's understand the physical meaning. Imagine fluid flowing over a heated surface. Near the wall, a thermal boundary layer forms. A thin boundary layer leads to strong convection, and it gives high Nusselt number. A thick boundary layer leads to weak convection, results in low Nusselt number. So the Nusselt number is basically a measure of how well the fluid removes heat from a surface. This is extremely useful in heat exchangers, electronics cooling, turbine blade cooling, automotive thermal management. Now let's talk about why CFD engineers care so much about the Nusselt number. 1. Validation of CFD results. In CFD, we often compare simulated Nusselt numbers with theoretical correlations or experimental data. If they match well, it means your mesh, turbulence model, boundary conditions are working correctly. 2. Local versus average heat transfer. CFD allows you to compute local Nusselt number, pointwise heat transfer, average Nusselt number over a surface. This helps identify hot spots, regions of poor cooling, design improvement areas. 3. Performance comparison. When comparing two designs, higher Nusselt number means better thermal performance. For example, different fin geometries, different flow velocities, laminar versus turbulent flow. Nusselt number gives a clean, dimensionless comparison. In tools like ANSYS Fluent, the Nusselt number can be calculated using wall heat flux, wall temperature, bulk fluid temperature. It's commonly used in post-processing to evaluate heat transfer efficiency. So to summarize, the Nusselt number measures the strength of convection. It compares convective and conductive heat transfer. And it plays a key role in CFD validation, design optimization, and thermal analysis. If you found this helpful, hit like, subscribe, and let me know in the comments what CFD topic you want next.